Welcome. It's wonderful to gather together with you in this way that is as real as any way. And I think one of the great things that has happened out of this not great pandemic is our ability to connect with one another in ways that are seamless and in a way much easier than our previous mechanisms. It's my great pleasure to welcome you to this event with one of our outstanding young faculty members who will describe her really top of the line research to us all. I am honored to be Dean of the College of Science. This is a fantastic college and it is on a fantastic trajectory. Our tagline is connects. It is short, it is easy to understand, but it is incredibly powerful. We think about connecting our work through the power of research, which really defines who we are. Research connects with education, where we educate our students in aspects of our research, and we also educate our students to become problem solvers, independent thinkers, and themselves researchers. We connect our research with innovations, with products that come out of our scholarship. And all of these three, the research, education, and innovation, connect with one another in positive, powerful ways. It is a fantastic set of connections. We also think about connecting our college and each department in our college with one another through cross-disciplinary research. We think about making those connections, and in fact, we make them very, very frequently across Northeastern. We make them across our community, and we make connections across the world. So our focus in this gathering is to think about research, which really is the driver of the excellence of our college. The framework today is focusing on the Department of Physics. And as I said, on one of our brilliant young investigators, Professor Toyoko Orimoto from the Department of Physics, and this fantastic image that she has challenged us all with to begin. Your connection with us as our audience, as our Northeastern community is extremely important. It is the community of Northeastern, of our alumni, our parents, our friends, that drives us forward in ways that focus on the togetherness, the working together of Northeastern and of our greater community. And I'm so glad that you have taken the time to spend with us today and to discuss with Professor Orimoto her groundbreaking research. And with that, I am going to, without further ado, introduce you to Professor Mark Williams, who is chair of our Department of Physics, a fantastic department whose focus spans the gamut of the tiniest particles to very large biophysical processes. It's a really wonderful span of scholarship that is covered by the physics department. And Mark, please, would you take over and continue with the introductions?
Great. Thank you, Hazel. Yes, it's a great pleasure as chair of the physics department to introduce Professor Toyoko Orimoto, a star researcher in experimental particle physics. Professor Orimoto received her PhD in physics in 2006 from the University of California, Berkeley. She was then named a Robert A. Millikan postdoctoral fellow at Caltech, followed by an appointment at CERN as a CERN fellow in Geneva, Switzerland. She started as an assistant professor in the physics department at Northeastern, here at Northeastern in 2012, and was promoted to associate professor with tenure in 2019. In addition to being a valued member of the very successful Compact Muon Solenoid, or CMS, experiment at the CERN Large Hadron Collider, she has also demonstrated leadership in the development of a major hardware component of the CMS detector known as the electromagnetic calorimeter. She's a recipient of the prestigious Department of Energy Early Career Award, as well as a subsequent major grant from the National Science Foundation to support her research in this area. Importantly, she also co-hosted in summer 2019 the American Physical Society Division of Particles and Fields meeting at Northeastern, which had over 500 attendees, and it was a major conference, and it's a really impressive development to be able to host such a large meeting at your own institution early in your career. She's a very accomplished researcher, and I look forward to hearing about her work. And with that, I'll let Professor Orimoto take over.
Thank you so much, Dean Sive and Professor Williams, for that incredible introduction. I really appreciate it. So again, I'm Professor Toyoko Orimoto from the Physics Department, and I am here to talk to you about exploring the smallest scales with the world's biggest science experiments. So for instance, the picture that you see here that Dean Sive has alluded to, that is a picture of the experiment I work on, the CMS detector, and it's about the size of a 3-story tall building. So I'll get into that in further detail in my talk. It's also the background of my, my Zoom video. So first of all, as Professor Williams mentioned, I study experimental particle physics. So before we dive in, I wanted to take a step back and describe what exactly that means. So first of all, physics. Physics is the study of the physical world and how it works. It sounds very broad, and indeed it is a very, very broad topic, which is one of the reasons I love it. And by particle, when I say particle, I don't mean particles of dust. I don't mean things that you can even see with your eye. What I mean by that are the absolutely smallest things in nature, the most elementary constituents that make up everything in the world. And by experimental, I mean that I build and run experiments to run tests of theoretical physics, so theories of physics. So I'm an experimental particle physicist. As I mentioned, and also as Dean Sive has kind of alluded to, physics is the study of the scientific study of the physical world, and it covers a very broad range of topics like you see depicted here. One of the things that I found deeply appealing and very satisfying about physics is that it connects this immense range of phenomena that seem totally different on the surface. The laws of physics govern the absolutely largest things imaginable, like galaxies and the universe, to the absolute smallest things imaginable, like atoms and things even smaller than atoms. And as Dean Sive has alluded to, our department actually conducts research on this very vast scale. But I, as a particle physicist, what I'm specifically addressing are the smallest constituents in nature. So what are the smallest building blocks of nature? That is the question that I ask myself every day as a particle physicist. So for instance, I think everybody loves cookies. I like to think that at least. So imagine what goes into a cookie. Well, I might argue that the most important ingredient in a cookie is sugar. At least that's the most important ingredient for me. And then when I look closely at a teaspoon of sugar, what I'd find is that sugar is made up of tiny sugar crystals, right? So you see, if you look closely there, you see little fine granular crystals of sugar in that teaspoon. But if I were to look even closer, what I see is that those small crystals are made up of sugar molecules. But as a particle, if you were a chemist, maybe that's sufficient for you. But as a particle physicist, I'm not satisfied with just that. I want to know what's inside that molecule. When I look in that molecule, what I see are carbon, oxygen, and hydrogen atoms bound together in this molecule. And what I want to know is what are inside those atoms. So for instance, if I were to take that hydrogen atom and look even closer, what I would see is that in the center of that hydrogen atom, what I'd see is a positively charged proton with a negatively charged electron zipping all around that proton. And yet as a particle physicist, that's still not enough. I want to know even more. So what I want to know is what's inside that proton. What if I were to look inside that proton, what's in there? It turns out if you were to look inside a proton, there are elementary particles called quarks, like you see depicted in red, blue, and green here. And those quarks are bound together by other particles called gluons. So inside a proton, we have these quarks bound together by gluons. Sorry. And as a particle physicist, you might ask, well, you said that that's not enough. Is there anything even deeper than that? And yes, in fact, it turns out that there are other scientists who are trying to find whether those elementary particles like up quarks, down quarks, gluons, whether those particles also have substructure. Hopefully that gives you a sense of how a particle physicist like myself thinks. I'm interested in the absolute smallest things that make up nature. So as a particle physicist, I believe that the universe, the stars, the planets, everything around us is made up of a small set of elementary particles. I believe that these particles are the basic building blocks or ingredients that make up all of the matter that we know of. Here I show you what I think of as kind of like a periodic table of particle physics. So if you think back to your high school chemistry class, you probably recall seeing the periodic table of elements. So for instance, there's hydrogen, helium, etc. And from those elements, we can make up all the matter that we're familiar with on Earth. The standard model of particle physics, which is the kind of technical name for this periodic table of particle physics, is very similar. It summarizes what we know about the elementary particles that have been observed and the interactions between those particles. So for instance, the particles on the left here, so the left-hand side, are the particles that make up matter. So for instance, you see this familiar electron that we talked about, as well as the up and down quarks that we find inside a proton. So the particles on the left make up the stuff, the matter. On the right, you see the particles that transmit the forces or interactions between those particles. So for instance, the photon's very familiar because light is made up of photons, and the photon is the particle that transmits the electric force between charged particles. And then also we have the gluon. That's the particle that I mentioned is what binds those quarks inside the nucleus. It's that very strong force of the gluon that binds those constituents inside those nuclei. On this next slide, I show you kind of a more modern conception of the standard model. This is the same particles, but depicted in kind of a more modern fashion. And the key difference here is that you see that this particle at the center, the Higgs boson, plays a very central role here. The reason for this is because the Higgs boson, which you may have heard about, is the particle that imparts mass to the other elementary particles. So the standard model of particle physics without the Higgs boson suggests that the elementary particles are massless. And I'll talk a little bit more about that in a little bit. But we know that the particles have mass. We know that the electron has a certain mass that has been measured. The W and Z bosons here, et cetera, those have masses. We know that particles have mass. So how do those particles acquire mass? Without the Higgs boson and the Higgs mechanism, the standard model that I described requires that these particles are massless. So how is it that these elementary particles acquire the masses that they have? What do I mean by that? Why do we need a theory to explain the masses of the particles? Why can't they just have the masses that they have? So why can't we just say the electron has this mass, the W particle has this mass? Well, one of the underlying principles upon which the standard model is built is symmetry. So it sounds very simple. It's sort of like the mirror symmetry that you observe every day. When you look in the mirror, you expect that what you see in the mirror reflection obeys similar laws as your own image, right? The standard model is based on very similar principles, and symmetry is one of the most important underlying principles for particle physics. And if I say that the electron just has the mass that it has, or the top quark has just this arbitrary mass, it actually breaks that symmetry of the standard model, the very foundation upon which it's built. So back in the 1960s, a number of particle theorists, including Peter Higgs, came up with a new theory to explain how elementary particles acquire mass. What they postulated is that there's a new force field filling all of space. So Peter Higgs and his colleagues postulated there is a new field filling all of space. And Einstein's theory of relativity tells us that massless particles travel at the speed of light, while massive particles travel at less than the speed of light. Let me say that again. Einstein's theory of relativity, which you may have heard of, tells us that massless particles, particles with no mass, travel at the speed of light, while particles with mass travel at less than the speed of light. And what's happening in this theory is that when these originally massless particles traverse this force field, they get slowed down to below the speed of light, effectively acquiring mass. It's as if the Higgs, this force field, also called the Higgs field, is like the sticky molasses filling all of space. And these particles, as they travel through space, they're interacting with this sticky molasses. So it's like if you were to throw a ball or fire a bullet through the sticky molasses, it would get slowed down. And how much these particles get slowed down by this new field is indicative of how massive it is. So a more massive particle gets slowed down more, and a less massive particle gets slowed down less. And it's through this mechanism, which we call the Higgs mechanism, through which the particles get the masses that they have. Now, this theory that Peter Higgs and company devised helps explain the masses of the elementary particles without breaking the symmetry, this very important symmetry of the Standard Model. But how do we provide evidence that this force field exists? How do we know that it's there, right? How do we know that it pervades all of space? Well, quantum mechanics, which is the physics of the very small physical world, tells us that all force fields have associated quanta. You can think of a quantum as a bundle of energy or like a disturbance in the force field. So a familiar example is the electromagnetic field. So you know about electricity, I think. That's the electric force that makes positive charges attract and opposite charges, like charges attract and opposite charges repel each other. That's the electric force. That force field has a quantum associated, and that quantum associated with it is the photon. The photon is the vibration of the electromagnetic field. And just like this, very similarly, the vibration of the Higgs field is the Higgs boson particle, right? The Higgs boson particle is like a disturbance in the field. And it's this disturbance, it's this Higgs boson that what we were searching for as evidence for this Higgs field. The Higgs boson is akin to a vibration in this Higgs field, and it is the Higgs boson that we searched for using this gigantic experiment. Here's kind of another analogy to think about the Higgs field and the Higgs boson. This is kind of a cocktail party, let's say pre-COVID cocktail party filled with physicists. I know that might not sound like a very exciting party for the average person, but that's the kind of party that I go to, physics parties. And suddenly in this party, a tax collector walks into the room. Because none of the physicists wants to talk to the tax collector, he makes his way easily across the bar, right? He has no interactions. I apologize to any tax collectors in this Zoom, sorry. But because none of the physicists wants to talk to the tax collector, he kind of goes very quickly across the room. In this analogy, the tax collector is like a massless particle. So he's kind of like a photon or a neutrino, something that has zero or very little mass. On the next slide, I have another animation. Here we have a physics superstar, Peter Higgs, walking into a room full of physicists. He would be swarmed by physicists eager to talk to him, and he would have to push his way to the bar. He has many interactions with this field of physicists as he walks across the room. In this case, Peter Higgs is akin to a very massive particle because he interacts so strongly with this field of physicists. So he's like a very massive particle. Now, last in my analogy, now imagine that instead of having a person go across the room, we now have a rumor spreading across the room. So we have a rumor like, who's going to win the Nobel Prize this year? There's a rumor traversing the room, and people clump together to hear that rumor. This clump of people, this disturbance in the field, is akin to the Higgs boson itself. It's a vibration of this field. The Higgs boson is a vibration of the Higgs field, just like this, a disturbance in that field, just like this rumor is a disturbance in this field of physicists in this party. So now that we know that the Higgs boson is the particle that we need in order to find evidence of this incredible mechanism, how do we go about discovering things like the Higgs boson? Well, we particle physicists build big machines to accelerate particles to very high energy. Ironically, in order to access the very tiniest things in nature, we have to go to the very highest energy scales, what we call the energy frontier. And in order to get to that energy frontier, we have to build very large machines in order to go to very high energy. When we accelerate and collide particles, Einstein's famous equation E equals mc squared, so E here stands for energy, m stands for mass, and c stands for the speed of light. Here, Einstein's equation tells us that energy, E, can be converted into other types of matter here, M, or other particles. So by smashing together particles at very high energy, what we're trying to do is to produce new types of matter using these particle accelerators. The particle accelerator that I work on is called the Large Hadron Collider, and it's based at the CERN laboratory in Geneva, Switzerland. So it's called the Large Hadron Collider because, first of all, it is indeed very large. It's about 16 to 17 miles in circumference. So this line here, it's actually underground, but this line kind of depicts where the Large Hadron Collider goes. It's so large that it encompasses a number of small villages and also straddles the French-Swiss border. The Large Hadron Collider, or LHC, is the world's largest and highest energy particle accelerator. You may have heard of the CERN laboratory in the Large Hadron Collider because it was featured very prominently in this movie, Angels and Demons. It was actually filmed while I was at CERN. As you may have also heard of the documentary Particle Fever. You may have also have heard of CERN because for a time, people thought that the LHC would create black holes that would destroy the Earth. Needless to say, that hasn't happened and will not happen. I promise you that particle physicists are very, we're pacifists. We don't want to destroy the Earth. Another reason the Higgs boson was a little bit famous is because it was also called the God particle, since it imparts mass to the other particles. Going back to the Large Hadron Collider, so we know why it's called large. It's enormous. It's 16 to 17 miles in circumference. It's a hadron collider because it collides protons. Hadron basically means a particle that's made up of quarks and gluons and interacts strongly through this strong force. And as I mentioned, the hadron being collided at the LHC are protons. These big blue tubes that you may have seen pictures of are superconducting magnets that accelerate beams of protons to very near the speed of light and keep them bent in this very large circle. In the LHC, we have counter-rotating beams of protons circulating many thousands of times per second around this collider, producing about 1 billion proton-proton collisions per second. And these proton-proton collisions happen at a few different interaction points along the collider. And my experiment, the CMS detector that you see depicted right here, is one of those places where those proton-proton interactions happens. So once we collide those protons and produce Higgs bosons, how do we actually observe the Higgs bosons? How do we record Higgs bosons and know that they're being produced? This brings me back to the giant particle detector that you saw on the first slide. This is the CMS detector, or compact muon solenoid detector, which I work on. And you may not have noticed it at first, but you see a person here to give you the sense of scale of the experiment. It is really enormous. It's about the size of a 2 or 3 story tall building. So particle detectors like this are placed at the different interaction regions of the Large Hadron Collider where the protons are forced to collide. And these particle detectors, you can think of them as like giant cameras, which are taking millions of snapshots per second. These particle detectors use different types of sensors in order to measure the properties of the particles, like the mass, the energy, the charge, the momentum of those particles as they traverse the particle detector. Now, Newsweek called us the biggest experiment ever. We are one of the biggest experiments ever produced, and also claimed that it's European. But in fact, with more than 1,000 participants from about 50 institutions across the country, the US is actually the single largest national group in the several thousand person collaboration that I belong to. So the US is a very, very important contributor to this experiment, despite the fact that it's physically located in Europe. My collaboration is so large that you can imagine how big our summer barbecues are. This is actually a picture from one of our summer barbecues at CERN several years ago, and you can see me pictured as a tiny person in the lower left. So this gives you a sense of the scale of both the experiment as well as the human effort involved in creating this enormous, very complicated experiment. Before I move on, I also wanted to show you a few photos taken at CERN of our own group members from Northeastern. So there are several faculty who work on the CMS experiment. So myself, Professors Wood and Barberis, Professor Skinari, who's the newest member of our group, And we have a number of graduate students and postdocs based at CERN who help us conduct this research. So you can see two of my graduate students in the control room of the CMS detector. And we also have co-op students depicted here. So here, Kelsey, for instance. One of the best things about my job, I think, is that I get to work with incredible undergraduate students who go to CERN for 6-month periods at a time working on the CMS detector. It's really a joy to work with these students. Now, going back to those snapshots of the Higgs boson, so the particle detectors are taking many snapshots per second, many millions of snapshots per second of the events that are going on. And here you see one example of such a snapshot. This is a potential Higgs boson event where the Higgs boson itself is very unstable, so we never actually see the Higgs boson by itself. It decays into other types of particles before we detect it. So it's those decay byproducts that we're looking for. In this particular picture, the Higgs boson was created at the very center of the detector, and then it decayed into 2 energetic photons, leaving these deposits that you see here in red in the detector. So this is a very classic signature of the Higgs boson, decaying into 2 energetic photons. So it's by collecting many events like this and looking at the byproducts of these decays that we reconstruct the process that may have produced the Higgs boson. It's events like this and many others like it that give us very strong evidence for the discovery of the Higgs boson. I'm going to skip this and move to the next. Actually, maybe I have time for, I'm going to show you just a quick animation of what those collisions look like. So here's the Large Hadron Collider with the protons accelerating through the Large Hadron Collider, colliding inside my detector to produce potential Higgs boson events. And I can show that again later if you're interested. It was events like these and many others like it, as well as evidence from the competing experiment, the ATLAS experiment, which gave us very strong evidence for the observation of the Higgs boson. So for instance, we claimed a statistical significance of 5 sigma. You may have heard that term 5 sigma before. So the significance of our observation was 5 sigma, which in kind of more simple terms means that the probability that we mistook the background as a fluctuation to fake the signal, the chance of that happening is 1 in 3 million. So we have very strong evidence that this was actual Higgs boson signal. And we made a very big announcement of the Higgs boson discovery at CERN in July of 2012, actually July 4th, 2012, where you see some of the people behind the experiment celebrating at CERN in this picture. So it was events like this, it was this observation that confirmed the theoretical discovery of the Higgs mechanism that led to the Nobel Prize being awarded to Peter Higgs, this person that discovered the Higgs mechanism with his colleague Francois Englert. They were awarded the Nobel Prize in Physics in 2013 for the Higgs mechanism. And a really important part of this prize was the fact that this theoretical discovery was confirmed by the experimental discovery by my experiment and the ATLAS experiment at CERN. So they won the prize for the theoretical discovery, but a very important aspect of that was the fact that there was experimental confirmation of the Higgs theory and the Higgs boson. Now you might say, okay, we've discovered the Higgs boson, so what are we doing now? What are we doing now with this large experiment? Well, even if the Higgs boson completed the standard model itself is not the final picture. It's not the final piece in what I call this great cosmic puzzle. It's just one piece of the greater puzzle. For those of us here who are scientists, we know very well that science isn't just about finding answers. It's about asking questions, finding answers, and then asking even more questions. So some of the big questions that I think are really important to answer are, for instance, why is gravity so weak? Why is gravity not included in the standard model? If you think back to that periodic table that I showed, for instance, the electric force, the strong nuclear force, but I didn't include gravity. Gravity is not part of this yet. So how do we include gravity in the standard model? Are there extra spatial dimensions beyond the 3 X, Y, and Z spatial dimensions that we experience? Do the elementary particles have further substructure? Where does the matter-antimatter asymmetry come from? So at the beginning of the universe, we believe that matter and antimatter were produced in equal abundance, but the stuff that we see is made of matter. So where did that asymmetry arise from? Are all the forces in this standard model manifestations of the same force? So some people think that there's a grand unified theory at a higher energy where all of those distinct forces will become one. And lastly, what I think of as one of the most important questions in all of science right now, not just physics, is what is the dark matter and dark energy in the universe? The stuff that I talked about for the standard model actually only explains 5% of the universe. The vast majority, 95, 96% of the universe is made up of dark matter and dark energy, which is stuff that we know very little about. So I think that's one of the most pressing questions in all of science, not just physics. And the Large Hadron Collider may have some insights into all of these questions. So that takes me to the kind of my last slide, which is the next frontier, the high luminosity frontier. So we're running the Large Hadron Collider till the end of about 2024. And after that point, we're actually upgrading the Large Hadron Collider as well as the detectors for a high luminosity phase. By luminosity, I mean the rate at which we collect data. The high luminosity LHC will provide us with an even larger data set in a shorter amount of time. And at the same time, it's going to present us with many technological challenges for the detector. So we're upgrading the detector during this time. And many of the people and students that I mentioned are involved in this upgrade. So hopefully with this upgrade and with the future runs of the LHC, we'll continue to discover new physics at this high energy frontier and answer some of these really pressing cosmic questions. Thank you.
Toyoko, thank you so much for that brilliant presentation. Really, it's the most accessible presentation of particle physics I have ever encountered, and absolutely fantastic. So thank you so much for this very clear way of communicating your groundbreaking and pivotal research. Great honor to hear you speak. I'm looking at the chat here. We did not specifically encourage you verbally to put your questions in the chat, but I sent everyone a note, and there are some questions in the chat. Please ask, and whatever you want to know, I know that Professor Orimoto will answer for those of us who are not particle physicists in her clear and accessible way. So let's see what we have so far. There's a question about how long it took to create the experiment at CERN. Toyoko, please.
Sure, thank you. Thank you for your questions. And like I said, I think questions are the most important part of science. It's as important as the answers. So as you can imagine, this experiment has took a very, very long time to design and build. So the initial kind of proposal for the detector came out in 1992. So we think of that as kind of like the birth of the detector. So it's decades. It took us, so let me think back. It's more than 30, it's about 30 years old, the experiment, the collaboration. And it took us so we started running in the early 2000s. So it took us more than a decade to build. Hopefully that answers. Yes, yeah. It took a decade and many thousands of people to build just my experiment. And there are others like it at the LHC.
It always seems to me so amazing and wonderful that this is such a cooperation of so many countries, so many universities and institutions, people at all levels across the world. It's the kind of unification of science that I think is such a brilliant manifestation of how to get things done together. Do you think does it work well, the experiment?
I agree. It's an incredibly huge undertaking. I can tell you that my collaboration is like its own nation itself. Like we have a constitution, we have a governing board, we have all these things to make it work. And I think it works well. I think it's an incredible example of how we can do science on a big scale, engaging many, many people and many, many nations and institutions.
Fantastic. And I thought your observation of the Northeastern co-op students who can get out to the experiment and to spend their time at CERN, what a fantastic opportunity that we sponsor our students to be able to undertake.
It's an I think it's an incredible experience for the students, but it's also an incredible experience for me as well. I think it's fantastic for everyone involved.
Brilliant. Good. Let's look at these very interesting questions that are coming up in the chat. Here's one. How do you know that you're discovering Higgs particles and not new particles?
That's a really good question. We didn't know at first, you know, so the Higgs boson, when Peter Higgs and his colleague came up with this theory, he came up with also predictions of how the Higgs boson would act. So for instance, I showed you a picture of the Higgs boson decaying into 2 photons. So the Higgs theory predicts very precisely how often the Higgs will decay into 2 photons, how often it will decay into other particles, etc. The one thing that we didn't know was its mass. And once you determine the mass of the Higgs boson, it basically will tell you, it predicts all the other aspects of the Higgs. So how often it will decay into this, what rate it is produced in this way, etc. And so once we pinpointed the mass, we were able to confirm that all the properties of the particle that we observe are very Higgs boson-like. But actually very early in its discovery, we weren't 100% sure. We thought we had very strong evidence that it was a Higgs boson particle, but we spent years subsequently confirming that all the properties of that particle were very Higgs boson-like. One thing that you may have noticed in my presentation is like, sorry, in this is the publication where we announced the discovery of the Higgs boson. And you see that it says first observations of a new particle in the search for the standard model Higgs boson. It doesn't say we discovered the Higgs boson, we discovered a new particle, right? It took many years for us to confirm with undoubtedly that what we see is the Higgs boson. So I think that's a very good question, a question that we asked ourselves for many years. But now we have very strong indications that it is indeed the Higgs boson. That doesn't mean that we're not going to see other new particles, but what we did see is very Higgs boson-like.
It's always amazing to me that, you know, we can, you, not me, we, the collective, we, can identify particles without actually, you know, seeing them under the microscope. I think it's extraordinary that there is this kind of reality that is built up based on inference and observations, you know, that's real and solid. I think it's just a extraordinary landscape of thinking about the world and the universe in ways that are different from our day-to-day experience of being able to see things and touch things. And that's, I think, what some of the questions are asking you here. There's a couple of ones that relate to dark matter. Let me try to bundle these. How do we know that dark matter exists? Can dark matter be a particle that we've already discovered? How can the existing experiment be applied to understanding dark matter? This kind of question of dark matter, as even the title, the name, you know, dark matter is so mysterious and elusive. You know, is it there? What is it? How do you know? How do you find out what it's made of? I think that's what all these questions are getting to together.
I'm glad that people have so many questions about dark matter because, like I said, I think it's one of the most important questions out there in all of science. I mean, we don't know what most of this stuff is in the universe. How do you sleep at night, right? Like, it just keeps people up, scientists like myself. So we know we have very, very strong evidence for the fact that there's dark matter out there, but from astronomical observations. So dark matter is matter that interacts gravitationally but doesn't interact in other way and interacts very weakly otherwise. And so we can make astronomical observations and see that the luminous stuff, the stuff that we can see like stars, only makes up a small fraction of the stuff that is producing gravitational attraction, right? So by making astronomical observations, we can infer that the luminous stuff, like the stars, only makes up a tiny fraction of the universe. So we know that dark matter is out there, but we have very little idea of what it is. It is very weakly interacting because if it wasn't, we already would have observed it. So it's very, very hard to observe. And there are many types of experiments that are looking for dark matter. So for instance, there's experiments that go to space and look for dark matter. There are experiments that bury deep underground looking for dark matter. And then there's also experiments like mine that are looking for dark matter. Because if dark matter exists, we think that it interacts with standard model particles. So although we haven't directly observed dark matter yet, we've made indirect observations of the fact that it exists. But we haven't actually directly observed it yet. But we think that it would, if dark matter does exist, we think that it will interact with standard model particles. And if so, if it interacts with standard model particles, we can potentially produce it at the Large Hadron Collider because of all of that we talked about today. The fact that when we collide particles at high energy, we can harness that energy to create new types of matter. But there's a lot about dark matter that we don't know. We think it's a particle, but it might not be. I'm a particle physicist, so my natural inclination, my bias is to think that everything is made up of particles, but it might not be. There are other theories out there, and we don't know what its mass is. We don't know exactly how it interacts. So there's a lot of parameter space that we have to cover. And the Large Hadron Collider has actually done a pretty good deal in kind of breaking down this parameter space and looking for dark matter. I think when we hopefully eventually observe dark matter, it's going to be evidence from lots of different sources. The experiments in space, those experiments underground, the experiments at the collider, that together conclusively will tell us that what we see is dark matter, right? If we get evidence from just one of those, we're going to be needing evidence from these other sources to confirm that this really is dark matter. Hopefully that answers some of the questions, but I think dark matter is one topic that can have very, very many really intriguing questions.
Very cool. Really, really cool. Let's go to a really crucial question regarding funding for the CMS experiment. And, for CERN in general, the question of funding research is, I would say, the most pivotal question in a way. We can ask very top quality questions and think about how to answer them, but the funding associated with them is always hugely challenging. And it is a challenge where, we look to multiple sources for the answers. We look to funding agencies at the federal level, at national levels, at the levels of foundations, and we look to our friends and alumni and parents for assistance with funding. It is the constant challenge of scientific research, how to gather the available resources in order to ask and answer these pivotal questions. So the question has come up, Toyoko, how the funding for the large project comes up. And of course, we fold into that the opportunities for our co-op students and Northeastern related type questions.
Yeah, so I can go back and show this little map that I had. So this kind of shows you a snapshot of all the different countries and institutions that contribute to the detector. So all of the nations involved provide funding for the detector as well as for the accelerator itself, the facility at CERN. And there are various kind of forms in which we get the funding. So I can speak specifically about the US. The largest contributor to the Large Hadron Collider projects from the US is the Department of Energy, but also the National Science Foundation, which is the source of my funding currently. And those are the two biggest, but the DOE is the one that provides the largest amount of funding. Some of the funding comes in terms of big project, huge grants that are aimed at kind of building, developing, upgrading the detector. And then we also get kind of smaller institutional chunks of grant funding, which is for funding things like graduate students, postdocs, et cetera. So we get these huge grants that are for the collaboration, for the experiment, that are mostly aimed at funding the building and the upgrading and the maintenance and whatnot. And then we also get smaller funding, like I mentioned, for funding graduate students, postdocs, co-op students also. But this is a constant negotiation when it comes to funding, as you mentioned, is a very complicated process that is sort of like a constant discourse between the funding agencies and the nation and the institutions, as well as the nations themselves. And especially for the high luminosity upgrade that I mentioned, this is kind of a really ongoing and important discussion that's happening right now.
Outstanding.
As I kind of alluded to, it's almost like funding a government, right? Like we have a constitution and we have very specific ways in which we receive and use the funding that we receive.
Yes, absolutely. I have a question from, the vantage point of being a life scientist. And, before your talk began, we were having a conversation about building life like ourselves from the units of cells. And then I said, we were thinking about how you build a cell. And one of the cool things about life, and it's absolutely essential for its function, is the three-dimensionality. It's we are three-dimensional entities. All our organs are, all of our cells are 3D. And in thinking about, and this 3D-ness is absolutely pivotal for life. When we think about where the 3D-ness comes from, we can think that molecules are themselves three-dimensional. And then we can push back and ask the question, are atoms three-dimensional? And where do you push back to in terms of elementary particles to understand when there is something that can be called three-dimensionality, that from which everything else arises? Does that make sense, that once you have something that's 3D, everything else is 3D because you're building with a 3D building block? And I'm wondering, in your experiment and in thinking about particles, where you can first say that we think this is a three-dimensional entity.
Yeah, that's a good question. I think that, so let me go back to one of my earlier slides. So I personally think that three-dimensionality comes at the level of an atom, kind of like what you were talking about. So thinking back about our cookie, it comes at this stage. We have that three-dimensionality. But when you think about elementary particles, I think of elementary particles as being point-like. So an electron is a point in space. It doesn't have a radius. It is just a point in space. Proton has space because it has substructure, but the most elementary particles like quarks and electron, I think of as being point-like. However, there are scientists out there who think that, who postulate that these particles also have substructure, that if you go into an even smaller scale, if we were able to access them, that even the elementary particles have substructure. So for instance, string theorists think of particles as being potentially like little strings, and vibrations of those strings correspond to different types of particles. Just like when you have like a musical instrument, different vibrations of the string produce different sounds, right? And so for string theorists, they think that if you look on an even smaller scale, it's not point-like, that there is dimensionality to like an electron, and those can be akin to like vibrations on a string. So I think that they're kind of two answers to your question. Like, I think in a basic level, I think of the three-dimensionality coming at the level of an atom, but because I think of elementary particles as being point-like, but there are scientists who postulate that even elementary particles, that the ones that we think of as being elementary, do have substructure and dimensionality to them. Like I said, there's no end to the questions that we ask as physicists.
Absolutely, absolutely. Thank you for that. That's a very, it's a very interesting question. I think, we could have a lovely discussion on if you put together a bunch of point-like entities, and they actually make something that's not point-like. Were they point-like in the beginning? I know nothing about this, but I think for me, it's a fascinating question. Question about the experimental approaches for incorporating gravity into the standard model.
That's a good question. So I kind of mentioned it a little bit at the end of my talk. Part of the reason why incorporating gravity into this picture is that gravity is so weak, and we don't understand why that is. That is one of the, in addition to the question about dark matter and dark energy, I feel like that is one of the biggest questions in physics. Part of the reason why gravity doesn't fit into this picture neatly is because the force of gravity, despite the fact that it is the one that we're most familiar with, the force of gravity is very, very, very weak. So for instance, compared to the electric force, the gravitational force is very, very many orders of magnitude weaker. And we don't understand why that is, and also how to bridge that gap of many orders of magnitude such that gravity can be incorporated into the standard model, right? Or like at least find some kind of cohesion between those two energy scales. It may be that that energy scale is so far away that it's inaccessible to us, or maybe one day we'll be able to build a collider large enough, higher energy enough, so that we can access that. But for now, it's one of the biggest questions. Why is gravity so weak? Why is it so distinct from these other forces in the standard model of particle physics? That's a really big question. The other thing that I mentioned about extra dimensions is one way in which we may be able to kind of bridge that gap. I don't think I have time to get into it right now, but extra dimensions. So by extra dimensions, I mean, normally we exist in this 3 dimensions of space, like forward, backward, left and right, up and down. So you can think of that as X, Y, and Z. But some physicists postulate that there are other dimensions of space, like 10 extra dimensions of space, etc. And that those extra dimensions of space explain why gravity is so weak. So that's actually one potential beyond the standard model theory that can bridge that gap about gravity. And I think that what you brought up again brings up a lot of interesting ideas.
Terrific. Well, these are, such important questions. And again, thank you so much, Professor Orimoto, for your very lucid, accessible talk that has left us enlightened and wondering, which are the 2 great currencies of scientific research. I thank you so much again for your talk. Thank you, Professor Williams, for introducing and for your work in the physics department. Our physics department is absolutely pivotal to the progression of excellence in the College of Science. And I encourage all of you to read through the flyer that we distributed to you that tells more about our physics department and about the opportunities to engage with support of the physics department. We welcome all of your engagement. We welcome your support and your involvement with the increase of our already excellent Department of Physics to even greater heights on the world arena. So thank you all so much for taking the time to spend with us, and we look forward to seeing you at the next Connects seminar.
Thank you so much.